Hello, this is the second part of video 11. I decided to make video 11 into two parts so that it doesn't become too long. So in the first part, I went over free fall and the first case of free fall, which was an object being dropped. And in the second video here, I would like to go over the second case of free fall, which is an object being thrown upward. So in this case, unlike an object being dropped where the initial velocity was 0, if you are thrown upward, then that means that your initial velocity is positive. So make sure to give a number greater than 0 to that initial velocity. A common mistake that I've seen is you have an object thrown upward and a student will still say that the initial velocity is 0. If it's thrown upward, it has to have some kind of initial velocity to make it go upward. Now, it is very similar to the object being dropped case though, because the acceleration is still negative 9.8 meters per second squared. Anytime you're in free fall, it doesn't matter if the object is going up or down, your acceleration will still be negative. The other thing I wanted to mention is that sometimes you'll have some symmetrical motion types of problems, and this is where the object is caught and released at the same height. So you can see a picture here. The object is thrown at A, it goes up to B, up to C, and it comes back down, back to E. So it's thrown at A and is caught at E. So this is symmetric motion. For this case, the time to go up equals the time to go down. That means the time here to go up, this is T up, it's going to be equal to the time to go down right here. This is T down. And the other thing about this symmetric case is that your velocity at which you are released, in this case this is the velocity at A here, is going to be equal to the velocity at which you're caught, which is the velocity at E. Now the only thing is that they're not quite equal like I have, because you can see that you're thrown upward but you're caught downwards. So really there should be a negative here because the speeds are the same but the velocities are in opposite directions. The last note I want to make about this is that the velocity at the maximum height is 0 meters per second. So right here at letter C, v equals 0. And this is because this is the point where the object turns around. It was going up, but in order to then go down here, it has to stop at point C. So just for that one instant, it does stop. This is going to be useful. Sometimes you have to break a problem in half, and you need to know what happens when it reaches the top. And this gives you an additional known variable that the velocity is equal to 0. Let's go ahead and do an example here. This one looks fairly complicated, but the way that I asked the problem here, it's really not too bad. There's actually many variations of this problem. So in this case, your ball is thrown upward with a velocity of 20 meters per second from the edge of a 50-meter building. How fast is the ball moving when it strikes the ground? So ignore all of the numbers that are given because in a problem they wouldn't be given to you. But you can definitely use them as reference to check yourself for this particular case. So this is a free fall problem because whenever you're thrown up or down or falling from rest, it's free fall. So we're going to use the kinematic equations. So the first step is to write down the givens. The initial velocity is 20 meters per second. It's upward, we're going to use up as positive. We know that when we're in free fall, the acceleration is always negative 9.8, so we can go ahead and write that down. Meters per second squared. And then we need a third given. So you've really got to make sure that you realize what part of the problem we care about. We care about how fast it's moving when it strikes the ground right here. And we are given some information right here when it's thrown upward from the building. So really, we really don't care about anything that happens up here. We really don't. That's just extra information. All we care about is the release point and the point at which it hits the ground. So this is what makes the problem easier in this case, because we can actually use this 50-meter height of the building here. That's going to be the displacement. The ball starts here and ends here. That's the displacement. Now technically the displacement is downward, so all we have to do is add a negative to this number. And this is the trick to making this problem much easier to solve is to realize that the displacement only cares about the initial position, the final position. It doesn't care about the whole path. It doesn't care about any of the stuff that happens above here. And now if we're looking for VF, the final speed or velocity when it hits the ground, then we have these three variables in this unknown. We can use that fourth kinematic equation that has these. V final squared equals V initial squared plus 2a delta y. And just like that, we can solve the problem by taking the square roots. This time, do not cross out V initial because it's not 0. You're going to be tempted to often cross it out, but really pay attention. And take the square root of all of this. That will give us our V final. So let's go ahead and plug in the numbers. V final equals the square root. And I'm not going to write the units just so that I have room to write all the numbers, but the units will work out if you plug them in. 2 times negative 9.8. And this is where it's very important to make sure that both the acceleration and the displacement were negative. Negative 50 for the displacement. Plug all of this in, and we're going to get 37.1 meters per second. Now, if we were solving for velocity, we would need to put a negative. As you can see in this picture here, there is a negative. But when the question says how fast, I interpret this as a speed. How fast is it going? It's going at 37.1 meters per second. So just to recap this particular problem, pay attention. If it wants to know what happens at the bottom, you can use this displacement and you don't care about anything that happens at the top. So perhaps later we'll do another example where we do care about what happens at the top, but I'll leave that for another video. We have one more thing in this video, a couple of your turn questions here. So the first one says a ball is tossed straight up in the air. At its very highest point, the ball's instantaneous acceleration, is it positive, negative, or 0? So I have this question just so that you pay attention to what is asked, because a lot of you will be tempted to say it's 0. But really pay attention. It's asking about acceleration. When you're in free fall, the acceleration is always, always, always negative 9.8 meters per second squared. So it's actually negative. If you said 0, you're probably thinking about the velocity. So really pay attention to what the question is asking. Let's do the last question. You're throwing a ball upward. If you throw it up faster, it will reach its highest point in less time. So you're going to be tempted to think that, well, if you're going faster, then you're going to reach things in less time because you're going faster. So you're going to think it's true, but the actual answer is false. So the way to think about this is that when you reach the highest point, you have to stop. So you're trying to get to velocity equal to 0. So let's say that you throw it up at a velocity of 9.8 meters per second. Well, your acceleration of negative 9.8 meters per second squared says that in 1 second, your speed is going to drop by 9.8 meters per second. That means that 1 second later, you're going to stop if you started at 9.8 meters per second. But now, what if you throw the ball up at 19.6 meters per second? Well, 1 second later, how fast are you going to go? Your speed is going to reduce by 9.8 meters per second. 1 second later, you're going to be moving at 9.8 meters per second. And then a second later, you're going to be stopped. You're going to lose another 9.8 meters per second. So you can see that the faster that you throw it up, the longer it's going to take to stop, because it's actually going to go higher when you throw it up faster. So if it goes higher, it's actually going to take longer. The initial speed being faster is what actually makes it take longer and go higher. So just to recap this video number 11, parts A and B, if your object is dropped, thrown downward or thrown upward, it's going to be in free fall. You're going to use the kinematic equations. Your acceleration will always be negative 9.8, and then you just have to figure out a couple more givens so that you can use the kinematic equations to solve for the unknown.